Hi everybody, welcome back. So what I'm doing right now is kind of getting things laid out to set up this rear panel. I just got a call from the powder coating company and the panels are complete, but I will have to go out there and pick them up in the next day or so. So in the meantime, I'm going to prepare this rear panel of the amplifier. The fan system I'm going to replace, and the soft start system I'm going to replace. And hopefully make it a little bit better and a little more modern. I'm going to use this board for the soft start, and it is going to monitor both capacitors on the cap bank. And when the total capacity or total charge of the two caps in series, which is your positive and negative differential supply, when it reaches about 96 volts, this will pull in. Now remember, there's positive and negative, I think 86 volts on this thing. So the total differential between the two is going to be over 170 volts. So when this thing's approximately halfway charged up, this will pull in and bring full power to the system. And the same thing, the dropout voltage is different than the pull-in voltage. So these resistors will also act to bleed down the capacitor bank when you turn the power off, because this circuit with full power on it will draw about 32 to 36 milliamps of current, and that will help bleed the caps down and help to put a little nominal load on it when it's first powered up, even though the amplifier itself should do that as well. So this should be pretty good. And of course you have this is a SL32 inrush current limiter, and that's going to be right in line with your incoming mains, which is down here. So this board will mount right here in place of all this stuff, which will be fine. This is a kind of similar idea to what my circuit does there. The only difference is it only monitors one leg of the power, and it kind of uses all this, this capacitor itself becomes the time delay, because it's actually not really looking at the cap bank as much as it's looking at the output of the transformer. It's a little bit different. I mean, technically, yeah, those caps can actually affect that, but this is, by changing this value, they can change the amount of time before the thing pulls in. You can kind of see here what they're doing. So this goes to the secondary of T1, which is, well, I'll show you right here. Goes up to here, and it goes onto the AC side. They rectify it, to a negative voltage with this diode. And yeah, I'm pointing with my finger. And it goes through this 5-watt, 300 ohm resistor. And this cap, as it charges up, you see it's right across this coil. It will cause a little delay before this pulls in. And then it will also act as a filter, because this is just halfway rectified, so you don't want this coil buzzing on you or anything. So that actually will smooth that out. So it serves two purposes, really. And then it bypasses the inrush current limiting resistor. So instead of using an ICL, they're just using a resistor for that. So it's not a positive temperature coefficient or negative NTC, I'm sorry. This will actually start out at a higher resistance, and the heat from it will actually cause it to drop in resistance. So if you just had this without the relay, it would still pretty much do the same job. I mean, it would be very similar. The only difference is it would get really hot and stay really hot, and it would, produce a lot of heat inside the amplifier, because these get pretty blistering hot when they're working. So the whole purpose of this relay is, just as this thing's heating up and the caps are charging up, this relay will bypass this inrush current limiter so that it never gets hot. And then there's a Zener diode, like a 24 volt Zener, because it's a 24 volt relay. and that just ensures that the coil across this never exceeds 24 volts. So depending on what voltage you have there, it just will cause these resistors to kind of cushion the blow. So they'll take up any excess voltage other than the 24 volts on the coil. And then this is just a steering diode, and what this does is this will ensure that you don't want to, if you connect it backwards, it'll block, it won't work. All right. Now, on top of that, I'm replacing the fan, and I'm putting a much quieter one in there, and you can see that it's running right now. And this is a really good quality fan, but instead of being $60 US, like the ones that people are recommending online, I found this thing on Amazon. It's by AC Infinity Products, and it is the Axial Series Project cooling fans. And I can tell you, for the price, I mean, this thing was, I don't know, maybe $20 or so. I forget what I paid for it, but it was way less than the other ones. And it has a nice big stator on it, so it'll run cool, and it's just dead silent when you put a resistor in with it. So right now, I have two 1.8K 10-watt chassis mount resistors in parallel. You can see they're paralleled to one another. And on normal, in normal function, this does throw quite a bit of air, but it's so quiet. I mean, I'll move my microphone. It's just so quiet, you can't even hear it. And then when you bypass this, it sounds absolutely like a jet engine. It gets really, really loud. So I'll show you here. I'll move over to here. And you turn this on now. And I mean, it's like huge amount of air it'll move. So it will cool this thing down in short order, if need be. And of course, there is a little thermal switch that can kick in that'll throw it into high speed as needed, and it'll cool it down quickly so it'll quiet back down. So I think this will be a good solution for this. I have some of that really high quality plastic from work that I still had some pieces left, and I machined a kind of a gasket for this. And I'm still kind of thinking how I'm going to do the mounting and all that. I am going to mount it to the back of the plate like this one, but I kind of want to tunnel it, the air flow through this chassis a little better. So the original one here had this gasket on it with all the foam is missing. And you can see it was actually physically a smaller diameter fan than this one. Even though the outer frame diameter is the same, you can see the blade diameter of this is actually a little narrower. This is just a newer design, and it works really well. And this is a plastic frame. This one's an all metal frame. So this is impedance protected. By the way, an impedance protected fan does not mean it's electrical impedance. They're talking about airflow impedance. And what that means is if you block one side of the fan that it can't pull static pressure, it's not going to load the fan down. It actually will kind of bypass as far as and it's all math formulas and everything, and it all has to do with the blade design and everything. But what it ensures is if you have a filter on it that gets clogged or something, it's not going to damage the fan. And it's not going to cause the air to swirl in funny ways or whatever. So anyway, I think it's going to be a good fit for this particular application. And I've just been doing this for a while because I just want to see how hot these run with absolutely no heat sink on them or anything. And while they are warm to the touch, I mean, I don't think I would be able to hold my finger there for long periods of time. They're not bad. And like I said, once you mount those to the chassis here, it's going to run really cool. Unlike this, it gets pretty hot. So again, some improvements. So let's get started on that, and we'll be back. Okay, so something really fishy is going on here. I'm disassembling this back panel. You can see I took the fan out and kind of just cleaned up the rust spots These grommets were just completely hardened and destroyed and rusted. So I have 4 new vinyl ones. Should last a long time. This resistor I took out and I'm going to replace with these chassis mount ones. I have some new RCA jacks that I'm going to use to replace the 1/4 inch phono jacks, or phone jacks I should say. And I have these rhodium plated carbon fiber speaker terminals, which are going to replace the old plastic. These ones are actually very good quality. I'm going to keep them because they're in decent shape. They need to be cleaned up a little bit, but they're good. And the only thing I have to do with this is there's a little tab there that's down in there, and I just had to file a tiny little notch. I tried one out to make sure it worked, and I'll be able to mount these right in place there. That'll be perfect. Here's where things get interesting. I was looking at the fuse holder, and again, all I did was cut these 2 wires. The rest of this is completely factory intact the way I got it. Well, it's not factory. We're going to find out why. This is that soft start circuit. So if you look on the schematic here, you can see the relay. You can see the little, the diode, the resistor. Here's the diode, the resistor. Here's the capacitor. All that stuff, you know, the 10 ohm, 10 watt. This is a 700 ohm, 5 watt. And that's this one right here, which is on here. They're showing 300 ohm, which is kind of strange, right? But nevertheless, that's what it is. And here's the thing. Here's our fuse holder. Here's your power cord coming in. The white lead, or the neutral lead of the power cord, neutral lead, how about that, is going to the fuse holder. The other end of the fuse holder, you can see they just have a solid piece of wire in there. The only thing connected on there, you can see very clearly, is this one wire. It goes to this terminal strip right here. See it? There is no other connection on this terminal strip other than this ceramic disc. And this is a 0.01 ceramic disc capacitor. This is a capacitor. It's not a conductor. It's a capacitor. The other end of the white lead is right here, and that's what goes out to the switch and to the power, you know, to power the circuit. And you can see that wire goes to the other end of the capacitor, and there is no other wire on that connector at all. So you can see, I believe this wire was supposed to go right here, and the black wire, well, the other end of the switch was supposed to go here or something. I don't know. But nevertheless, I don't see how we can get, I just don't see how you can get power because the switch is not connected there. In other words, going back to this again, here it is. This 0.01 is supposed to go across the switch terminal. Am I pointing to it right here? And you should come out of the fuse into one side of the switch, out of the switch, and to this 10 ohm resistor. That is certainly not what we have here. You're coming out of the fuse and you're not going into the switch, and then you're not coming back from the switch. You see what I'm saying? So this could never have worked this way. So the only thing I can figure, and you can see the bubblegum solder on this back here, right there. Somebody put that on there. And I don't know if somebody had disassembled this and then just hacked it back together or what, but this whole thing is miswired. At least that part of it is. And this is what you never know what you're getting into when you get somebody else's work when they were there first trying to fix something. Doesn't matter because all of this is being removed. I think it's hysterical. They have this massive power cord. Like I said, this is what you use on a window air conditioner unit. And then you have these tiny little wires coming out of there. powering the whole circuit. You know, again, I'm not going to get into it. I'm going to make it right, and I'm going to get this stuff out of here. Okay, things are coming along pretty good here. And I have the new soft start board fitted in place, and it looks a lot nicer than that mess that was in there. And I have to add one more wire for the return lead from the switch. Here's our neutral and hot going out. Here's our two monitor wires going to the capacitor bank for the bypass circuit for the soft start. But here's my favorite part. I got these nylon, or these, what are they? Vinyl O-rings in, and I have this little spacer that I machined out of that plastic. I'm going to mount it there, and that's going to kind of shim that out a little bit, the fan. And my favorite thing is this little thing. So I just cut a piece of bar stock aluminum, and I had this teeny little 2mm M2 tap. It was the only one I had, and for these teeny little cute screws, and I was able to thread and tap some holes in here and use some like computer, you know, laptop computer screws to attach this in here, and you can see they don't protrude through. And then I tapped an M3 hole, which is going to go right in here. I can flip it around a little bit, give it a little there. That's how it's supposed to go. Isn't that cute? And then I'll get a little bit of heat sink schmutz and put a dab of that underneath here, just a little bit. And then I'll screw that in with an M3 black oxide screw that will match the back of the cover. And that should give us our dropping resistors for the cooling fan, which is going to be very cool. No pun intended. Yeah. Puns and dad jokes, I'm terrible at it. All right, there it is. And then the fan can go in here, and then this will feed the power to the fan. And that should be it. And then I'm going to put a little bit of filter material. I think I have some stuff left over from a computer build a while back. I'll use that just to add a little filtration to the input and keep people's potato pickers from getting in there and hitting the blade. And this is coming along really, really good. All right, well, the power cord is in fairly good condition other than being really dirty. So I'm going to start out by cleaning it off with just some Windex, some window cleaner, glass cleaner, because that's what I have handy right now. There's lots of different things you can use, but I'll show you what I'm going to finish up with. And the little inserts that go in the back of the fan here and all the hardware are taking a little bath in evaporust. So we're let the evaporust do its thing. It works really well. And clean this cord up. But the idea with this, I mean, this is silly. Marantz did this with the 2600 and the 2500 also. Used this giant cord and then used the little tiny wires inside there after they fooled you with this one. I'm sure people will say they could hear the difference of this cord though. I personally can't hear power cords, but hey, some people can. My hearing isn't that good, I guess. Or maybe my caring isn't that good either. I don't know. I like good sound. I don't know. Weird. That is a crazy looking power cord. Hopefully I don't spray the lens of the camera. I'll just clean this off and then I'll be back. So, I don't know if I hit the record button or not, but I'll say this again. So I used Armor All Protectant, this is stuff you can buy in the automotive stores. It's for vinyl, you know, for doing the dash of your car or for the tires and so forth, plastics and vinyls. And I just put a nice coat of that on the power cord, and I'll let that cure and dry, and it'll just leave that kind of nice sheen to it, and it'll add some protection to the plastic to keep it from deteriorating or cracking. Okay, the Evapo-Rust did a pretty good job on this. It did leave a little bit of pitting, but hey, that's to be expected. These were pretty heavily rusted from this hardened, rusty plastic stuff that they had in there. So anyway, these are going to go right in here from the bottom, from the outside like that. And then this will go over top. And that's going to be how this thing's going to mount. And then the fan will go on top of that. And hopefully everything will work. Okay, it's all done. So you can see I have the inputs put in, the new rhodium plated speaker terminals. I put some screen on here, and it's just held on with magnets so it can be removed easily, and we're all set. I think it turned out okay. Like I said, this one I did not send to the powder coating because obviously all the labels and things, I didn't want the little screen printing to get messed up. So we're going to do one last thing before we close out this video, and that is I'm going to just do a quick preliminary test to the amplifier modules. And if they power up and we can get some bias on them and everything, then I'm going to end this video here, and I'll show you what we're going to work on next. And in case I didn't show it, here's the rear of the panel. And I still do need to mount the speaker protect board, but I'll figure that out a little when I get some more things put together, because I kind of want to make sure I get the positioning of it and everything correct. Okay, so I have this first channel hooked up, and it works perfectly. A couple things. I'm really not excited with the way they have you do the bias adjustment, so I think we're going to do it a little bit differently. We'll get to that in another video. But you can see these test points, R, S, T, and U. Those are directly across the emitter resistors of the outputs. And we can therefore measure the actual current flow through each of these legs, these parallel legs here. And what I did was, you can see the 4 screws. Those are the actual test points there. They're real test points. So I put little terminal strips on there, or little terminal lugs, that will allow us to attach the meter right across that, and we can actually measure. Now we could just as easily hook to the resistors themselves, but those are neat little test points that we can have. The plus and minus voltage are these 2 terminals here, and I marked them with red and blue paint. And then your ground terminal is there. Speaker output is right here, and I have the meter right now connected to one of the bias points. So we should be able to, when I turn the power on, we should see some millivolts as I go up. So there's plus and minus 12 volts. You can see we're already getting a little bit of bias. If I go up to 20 volts, and you see you get to a certain point where it should kick on here, and we should get some bias voltage. And there's not a whole lot right now. Let's see here what we get. There we go. 4.5 millivolts. And that's about, you know, it's very low right now because I don't even have half the rail voltage that should be here. I have plus and minus 31 volts. It should be plus and minus 86. So I wouldn't expect much bias voltage at all. And if I move over to the other set of test points, Let's see here. And it's about the same, 5 millivolts. So they're balanced pretty well. It tells me the two sets of transistors. If we go to the ground, if I can get my probe to behave, and I go to the speaker terminal, and you can see I have a little bit of DC offset there, so we should be able to adjust that. Let's see if it'll adjust. And that's acting a little bit funky. I'm not able to change that very much, so we may have to play with that a little bit to get it to work. So there might be something going on there, but we can do some testing. And again, we may not be able to get it to do that to adjust because I don't have enough voltage on there. I probably need, closer to the maximum voltage to be able to get the correct offset adjustment to work. Well, the one channel worked, but when I got to this one, I had basically a whole DC rail, the whole positive rail on the speaker terminal, telling me something's not right in here. So let's turn this on and kind of look at some of the voltages here. And we will listen to some flute practicing, I guess, upstairs. So if we look on here, so we first of all check our rail voltages. There's your negative 19 or 20 volts. There's your positive 20 volts. So we got that. If I go, it's always good to kind of start at the beginning, because if you have crazy DC offset, it's usually something going to be in the front end. And so looking at Q301 and 302, that's your input pair. That's kind of a buffer. So that's going to be these two right here. So here's the base of this one. And this is of Q301. And you have just under a volt on the base. Let's see here. And the collector, let's see. Is that collector? Or is this collector? I think there's collector. Either way, I should be seeing something more than that, because if you look, you have your 5.6K and you have this 4.3K. So let's make sure we have our positive voltages getting in here first. So there's your 20 volts. So it's about 8 volts when it gets down to here. We get down to our 5.6K, which is our 305, which is, I think, is it this one? No. Let's see where that 5.6 is. Is that this one? Yeah, 5.6K. All right. And then let's look at the 6.2K, which is coming down here. So there's the other 4.3K. Let's look on this side. And I have positive 8 volts on my negative. Am I looking at that right? So there should be, here's your negative 86 volts, but we have 20 volts right now. By the way, it's not drawing any current at all, just a couple of milliamps. It comes through here, and I mean, other than this 10 ohm resistor, what is this? 10 ohms, half watt. I should have 20 volts there. Well, minus the 10 ohm, or, well, if there's no current, then there should be no drop there. So where's that 10 ohm resistor? So there's positive 8 volts. There's 20 volts. That's a 10 ohm resistor there, half watt, 20 volts. What? I have negative 20 there, and I have positive 8.8 there. That resistor's open. Has to be. All right, let me... Are you kidding? I actually missed that. I swear I tested those, but maybe I didn't. I missed that one. Okay, let's go to ohmage. It's open. It's open. How about this one? Yeah, 10 ohms. How about these ones? 10 ohms. 10 ohms. Yeah, that resistor's open. I'm going to have to replace that. Let's see if we can do an above board replacement. Okay, let's get this Bessie. Here we go. 10 ohms. I got 2 of them here. I might as well replace them both. I think those will work. Okay, so I have a shirt with no collar, so it's like the little furry thing on top of the tribble on top of the microphones keeps rubbing against my chin, so if you hear a bunch of weird noise, that's probably what it is. Alright, so let's start over here. And yes, I have the power all turned off and everything. Let's heat this up. And this is that board that was impossible to solder on. So far, this isn't so terrible. Alright. And then let's see if we can persuade this to come out. Kind of. Ooh, I got that one. See if I can get this one a little better. Need to reflow it. Don't have enough solder down in there to get it. Nope, I got it. Okay. This is for lazy people that do not like to take all this stuff apart. So here we go. Now it's imperative that we get the leads trimmed down. You don't want them to protrude very far below the board, obviously. So that should be good right there. The nice thing about plated through holes is you can do this sort of thing. When you're dealing with ones that do not have the plated through holes, this is a little more difficult. You can still get the solder to wick down alongside the lead, but it's a little bit more tricky to do that. That other one's probably still good, but what the heck, while we're in there, we will do that. And I put a little melty spot on the corner of this capacitor. Oh well, no harm, no foul. It'll work. It should still capacitate. You know what? Like I said, while I'm at it, let's just replace this one here. Because we can. Let's see here. You kind of learn how to do this sort of thing when you get stuck with circuits that are really hard to get the board apart or whatever. You don't like, you don't want to have to spend forever tearing it apart. And if you have, like I said, if you have the plated through holes, there's no reason you can't do this. And it's just as good as a... There you go. That one. It's good to have a good solder pump too. These work really well. sometimes this heats it up better than the actual really expensive desoldering irons and stuff, believe it or not. There we go. Okay. Let's do a little fingernail pinch. And then I will, again, give this a little snip. Put this in. We're going to do this all real time here. Okay. There we go. Get that lined up. Try not to melt this capacitor. This one here kind of sunk down a little bit. Let's clean that up. Good. Okay, let's measure and make sure we have 10 ohms now. $10 ohms. 10 ohms. Again, I'm not getting on it because of the flux and everything. I should probably clean that. There we go, 10 ohms. Good. So let's just give that a little cleaning. Get some alcohol here. And just clean off some of that flux. Really doesn't need to be cleaned off, but make it neat if we can, right? There we go. Okay. Let's go back to where we were and see if we have some better luck with our voltage. Okay, we have our 20 volts back. So let's see. Wow, look at that, 20 volts. Yep, positive, negative. Haha, negative 14, positive 8. And what do we have up here? Look at that, no offset now. Can we adjust this a little bit? Yes, we can, look at that. And again, this is not going to balance until I get the proper voltage on there. But it's working, that's good. And let's come off of here. Let's see if we have any kind of bias going on right now. Like I said, it's 1/4 of the voltage that it should be right now. So we're running this really cold. But you can see I do have some bias voltage there. 2.7 millivolts. If I adjust it, it goes up a little bit. Goes back down. I turn it. Okay. I think it's working. Again, this is just a rudimentary test. Until you get full power on it, until you get it installed, you don't really know for sure. But I think that was the main problem. Again, I could feed a little signal into it, and we could do that. Let me do that real quick, and then we'll finish up this video. Okay, I have the little janky signal generator on there. Let's go up to our scope. I'll just move the camera there. Let me turn up the signal and look at that. I'm on 5 volts per division. You can see I'm getting plenty of signal. And it's clean too. There's my 1 kilohertz tone. So it works. So the amplifier's working. That's all we care about right now. Okay, that's it for right now. I'm going to put this back together and get it off the bench. And next thing we'll do is we'll work on the metering circuit for the next video. So until then, I wish you all peace, joy, happiness, and good health in your lives. And we'll see you again real soon. Take care, everybody. Bye-bye.